Hi everyone, I'm currently stood on a beach in Prestatyn in Wales. You might think I'm absolutely insane. Why am I walking in the sea in December? And the answer is probably I am a little bit. The water is freezing cold. Today I'm here to talk to you about waves. Now, waves include those that we can see right here, right now, the ones that are almost sweeping me off my feet, but they also include a whole load of other waves. And waves are really important to the ocean and all the processes within it. The way I would explain a wave is that it's just the propagation of energy forwards rather than the propagation of mass. So you might see these waves here, the ones around me. They move more upwards and downwards, but not really moving forwards. So a wave is usually defined as eta xt equals a cos kx minus omega t. So that means eta is the height of the wave, a is the amplitude, k is the wave number, which is 2 pi over the wavelength, omega is the angular frequency. Waves include all sorts of things from gravity waves that we've got here to much more complicated, larger scale types of waves. So that includes Kelvin waves, Rossby waves, other Poincaré waves, which we'll get onto very soon. So from the wave equation, we can find out the phase velocity and also the group velocity. So the phase velocity is defined as omega over k, and the group velocity is defined as d omega over dk. The similarities and differences between these two numbers, c being the phase velocity and cg being the group velocity, is what defines the dispersiveness of the wave. When I say that the behavior of gravity waves depends on the depth of the water, I mean that there are two different forms which we can sort of think about. So we've got deep water waves and we've got shallow water gravity waves. In deep water, where the depth is more than half a wavelength, the dispersion relation is omega squared equals gk. This means long waves travel faster than short waves. They are dispersive. That's why storm swell arrives as long, smooth waves first, with short, choppy waves afterwards. In shallow water, where depth is small compared to wavelength, the dispersion relation becomes omega squared equals gh k squared. In this situation, group and phase velocity are the same, and they are defined by root gh. This means that shallow water waves are non-dispersive. Whenever the phase speed depends on wavelength, we call the wave dispersive. Deep water waves and Rossby waves are dispersive, whereas shallow water waves and Kelvin waves are mostly non-dispersive. This difference shapes the entire behavior of ocean basins. Okay, now let's think about the Earth in a rotating frame. So, when we're actually in a rotating frame, the Coriolis acceleration has an effect. For inertial waves, if there are no other forces acting on it, they will create circular oscillations with a frequency of f, which is the Coriolis parameter. Where I am right now, which is about 53.3 degrees north, the inertial period would be about 15 hours. However, at the equator, this relationship breaks down because the latitude is 0. This creates all sorts of interesting dynamics at the equator. This means there are no inertial oscillations. Now let's think about Poincaré waves. These take into account gravity and inertial behavior. When both gravity and Earth's rotation act as restoring forces, we get Poincaré waves, which are gravity waves acting in a rotating sphere. Their dispersion relation looks like shallow water waves, but with rotation added. This is omega squared equals f squared plus gh k squared plus l squared. This tells us two things. They oscillate at least as fast as the inertial frequency f, and for large scales, rotation dominates. You won't see Poincaré waves at this beach because their wavelengths are approximately hundreds of kilometers. They're hugely important in places such as the Arctic, where they have a huge influence on sea ice edges. Here's something we can picture at this beach: Kelvin waves. So Kelvin waves are waves that move along boundary, controlled by the rotation of the Earth. In the northern hemisphere, a wave will always move with the boundary on its right. In the southern hemisphere, it will always move with the boundary on its left. At the equator, Kelvin waves behave differently. The boundary is provided by the equator itself due to the Coriolis acceleration being 0. This causes equatorial Kelvin waves. These are what has a huge influence on the El Niño southern oscillation. Kelvin waves are non-dispersive and incredibly fast. Now let's talk about Rossby waves, which move according to the beta effect. The beta effect is how the Coriolis parameter changes with latitude. These waves are slow and planetary scale. Their dispersion relation in a barotropic case is omega equals minus beta k over k squared plus l squared plus 1 over r squared. Rossby waves have key three features. They always move westward, never eastward. Rossby waves are strongly dispersive. This means that long waves outrun the short waves. Rossby waves control the adjustment timescales of the ocean. The Rossby radius, r, sets the scale over which rotation dominates over gravity. R equals root GH over F, F being the Coriolis parameter again. R is dependent on depth and latitude. These waves require a horizontal depth much greater than the vertical depth. In mid-latitudes, it's around 30 kilometers. At the equator, it's enormous due to zero latitude, which is why equatorial waves behave so differently. Now let's conclude by bringing everything we've just said all together. So, I've just been speaking to you about waves, and these waves that you can see behind me, these gravity waves, are just one part of a huge wave system across the ocean. So waves, they can include these shallow water gravity waves, deep water gravity waves, Poincaré waves, Kelvin waves, Rossby waves, and all combinations of the above. So the waves that I've just spoken about, there's so much more to say. There's so much more that I could have covered. They're really interesting, and I hope you've enjoyed learning along with me. Thank you for listening to my presentation, and I hope you've enjoyed learning about waves.